So at this point, we need to start talking about a little bit of terminology. And one thing that you're going to come across is this term definite integrals. Okay, now you may remember that we touched briefly on indefinite integrals last year, which was related to anti-differentiation, and we will go back and revisit that very shortly. But for the moment, just looking at definite integrals, the definition of a definite integral is that it's the area under a curve f of x between x equals a and x equals b. Okay, and it's written like this. So you would remember from last year we've got this funny curly sort of S thing, which we read as anti-differentiation, but is also used for integration, and we will explain the sort of the fine difference between anti-differentiation and integration. But what this means is that you're integrating between x equals a and x equals b of the function f of x with respect to x. So that's finding the area under the curve, so between this, whatever the graph of this function is, and the x-axis over this interval. Okay, there are a couple of provisos here on this one. F of x needs to be a continuous function on this interval, and f of x needs to be positive for all values of x in this interval. Now we do get into more complicated functions where these are not the case, a little bit further down the track, but this is what we'll sort of hold on to for the moment just to simplify things. Okay, we talked earlier about the limiting process, and that how we make this more accurate is by limiting the width of these columns as close to zero as we can get, basically. So it's related to the limiting chord theorem for differentiation, when we started talking about the difference between the points that we picked on the curve, trying to limit that chord. So this is similar, and it's written like this, which looks as scary as all get out, but it's really not that bad. Okay, so this is the denotation or notation that I showed you in the previous slide. So we're integrating between a and b. So if we're saying for this one, we'll probably look at, looks like it's going from 0. So from here, a to b, integrating between there. This is f of x, this curve. Okay, and we just want the area under this curve. Okay, so we're saying between a and b, what is the area between f of x and the x-axis? Now what this means is that we want to limit delta x, so this is a little symbol delta x, we want to limit that to 0, and delta x is the width of these columns. Okay, so that width in there, like that, that's delta x. So we're trying to make that as small as possible. Okay, now for each of these columns, the area, so the area of the column is going to be delta x, so that width, times the function height, so the value of the function, times fx, which is what we were doing in that previous, in the examples before that I was showing. Okay, so just the width, delta x, times the height of the function. Now, this is saying that we want to sum that over all of these columns for whatever width we choose. Okay, so however many columns we choose, so we're going to divide this into n columns between a and b. That's where this n comes from. So however many of those there are, we're going to add them all together. Okay, so basically this is narrow columns, as narrow as you can get. So saying that we want delta x to be as limiting towards 0, as close to 0 as we can. Okay, this is your height of the column at each point, the value of the function at each value of x. So that's your height of column. Okay, this is your width of column. And then this is your sigma, your sum, and that just means add it all together. Okay, so it's just a shorthand sort of way of writing. Doesn't matter how many columns you split it into, you just want to work out what is the area of each one based on the width and the height, and then add them all up together. Okay, so don't be too turned off by that sort of scary looking equation there. It's really not as complicated as it looks. Alright, so let's get stuck into a couple more examples. Now at this point we're just doing these ones geometrically. Okay, I will show you how to do them on the class pad as well. We go into the calculus techniques of how to do it and how it relates to anti-differentiation a little bit later down the track. But for the moment it's just getting used to the idea of actually calculating the area under a curve, so between the curve itself and the axis. Okay, so the first thing we need to do is draw a diagram. Alright, we like diagrams, draw diagrams. Okay, if you can't draw it yourself, draw it on your class pad, but whatever the case, get into the habit of drawing them. Okay, you can get tripped up a little bit further down when they get a bit more complicated, and it's a really, really good idea to have drawn it so you can see what you're looking at. Okay, so for this one, this is a really straightforward linear equation. Ooh, wonky axis. Okay, we know that it's going to go through -1 and 1 like this. Okay, so that's 1. This is going to be 3. Okay, if that's 3, and the gradient's 1 for 1, that'll be 2. Okay, because we've basically got a width here of 2, so we've got a height of 2. And we are trying to find the area under the curve from here to here, which is this triangle here. And triangles are easy. We know how to find the areas of triangles. Okay, so the area is just going to be half the base times the height. And in this case, both the base and the height are 2. Therefore, the answer is going to be 2 units squared. So mathematically, the way we write that is that the definite integral between 1 and 3 of x minus 1, and I tend to like to put those in brackets, with respect to x, is 2. Okay, and you can do this on your class pad. Okay, so we can go x minus 1, and then if you highlight it, go up to interactive calculation, pick the integration symbol. Okay, you might have played with indefinite integrals last year. We want to do definite this time, and we want to put in limits. So that's between 1 and 3. Okay, and limits that we've got here, and we go okay, and it tells us the answer is 2. And you can see that it's written in here, between 1 and 3, x minus 1 dx. Okay, so that's how you can do it quickly on your class pad, but I really can't emphasize enough how important it is to have some understanding of what you're actually looking at visually. So where is the area that you're trying to find, what sort of graph it is. So really do draw diagrams, don't just rely on your class pad to work it all out for you, because you will come unstuck. Okay, so the second example, this one we've got the same limit here, so we already know the answer to that, we know that's 2. And then we've got another one added in here. I'm going to draw it anyway, because it's good to see what's going on with both of these. So we've got 2 linear functions. Okay, we know that the first one went through these points like this. Now it just so happens that the second one actually has the same x-intercept. Okay, and we know that it's negative gradient and it's gone up one, so it comes down like this. Okay, and we're trying to find, so between 1 and 3, so that's 1 and 3, we already found that one. Okay, and then from here we're going from -1 to 1. So that's here, -1 to 1. So we've got this area now added here that we want to find, and it's actually the same, because we've got a distance of 2 from there to there, from -1 to 1 is 2. Okay, this we know will go up to 2 here, because it's a gradient of 1. -1 rather. Alright, so the area of this one is also going to be 2. And that's our half base times height. Okay, so then what we say is, therefore the sum of the integrals, because you're just adding them together, so you're adding those 2 areas, it's just 2 plus 2, which is 4. Really straightforward. Okay, so we're just adding to this previous area that we found before, we're adding this one. Okay. Again, on your class pad, so with this one, because you've got 2, you can actually go through and do it with the keypad, so I'll show you how to do that as well. So if you go to Math 3, note 2, you've got the integral here. Alright, so we can go, we want to go between 1 and 3, we're doing x minus 1, and it's dx. Okay, and then we're saying plus, and we'll do it again. So this time we're going from -1 to 1, and it's 1 take x, still dx, go, and it gives you 4. Okay, so you can do all this sort of stuff with your class pad like that. Okay, so in summary, integration is used to find the area under a curve. It is related to differentiation and anti-differentiation, but we'll talk about that a little bit later. We generally approximate it using rectangles, at least to start with, and then we limit the width of the rectangles to 0, and that will provide a more accurate estimate. A definite integral is the area between 2 points, the area under a curve between 2 points on that curve, and it's given by this notation. Okay, so get used to this notation where you've got integral a to b, some function with respect to, okay, dx, or whatever your variable is for that.